All right, guys, so what we're going to be talking about here is we are going to be kind of building on all of the ideas that we talked about in the previous unit, kind of tying those together and having them lead us into where we are headed in the future. So just kind of keep that in mind as we move forward, that a lot of the ideas we're going to be talking about, we previously talked about, now we're just tying all of them together. So the first idea that we do need to talk about is what the average rate of change was. Now, a lot of people are like, okay, I remember how to find average rate of change. We said it was like y2 minus y1 over x2 minus x1. And we have this interval that we are given right here. Those should be brackets. And those are x values. And so what this is saying on this graph is if I start at -1 on my function and I go to where x equals +2, if I find the slope that connects those 2 points together, then what I have found is the average rate of change. Now, we did call that there was another way to describe that, and it still is average rate of change, but that was also known as the slope of the secant line. Remember, a secant line is a line that has 2 points that exist on the function, and when we're finding the slope of that line, it's really easy. We can just say, okay, in this case, I can see the x value is -1, the y value that goes with that is 2. Over here, the x value is 2, and the y value is 5. And then we just find the slope between those 2 points, and we know how to do that. That's not that big of a deal. Now, by itself, average rate of change in these instances when we're looking at a function really isn't that big of a deal. But it's going to lead us into an idea that we're going to be talking about that is a very big deal. And so we need to change just barely. We barely need to change our definition of how to find the slope. Instead of calling our y values y2 and y1, we're going to say, and it really does mean the same thing, I'm going to call it f of x2 and f of x1. That just means I'm going to plug my x value in to find out what my y value is at each of those points. But really, that is what a better definition for what we need, where we're headed, a better definition of slope. Specifically this particular function where we're using the same function to find both y values. So you might be saying, okay, well, why do we want to do that? Why do we care what that definition is? Well, let's say we had this function, same function, x squared plus 1, but instead of wanting to find the slope of a secant line, let's say we wanted to find instead the slope of a tangent line. Now, the way that we find the slope of a tangent line is going to be a little bit different, and here's why. Because a tangent line, it was really easy with a secant line to find both of the x values and both of the y values. The definition of a tangent line is a line that only touches our function at one point. So it kind of looks like that, and that's not exactly right, but that's pretty close to what that line would look like, where I have a slope that I'm trying to find of this function, but I have an issue. Like I can see on this graph that the point 1, 2, we found that on the previous, well, it was -1, but 1, 2 exists on this function, and I've drawn that in a slightly incorrect place, but we know the point 1, 2 exists on the function. And I want to find the slope of this line. To be 100% honest, when we talk about calculus, when we talk about a lot of things in real life, the slope of that tangent line, even though it doesn't seem like it's important, is actually one of the most important things that we talk about in all of mathematics. So obviously there's got to be a way that we're going to find that. The problem is if you think about it, initially you're like, well, we're going to run into an issue. Here's the issue we're going to run into. I don't have a second point. Like I could guess, maybe you want to guess and say like, well, that point right there, when I drew this line kind of looks like 0, 1/2, like that might be it. Or maybe over here, it kind of looks like the point -1, -1 is on the graph, the way that I've drawn it. But those are guesses. Like I know one point that's on the graph, 1, 2 is on there for sure. Another point would be a guess, and we need to actually be able to find out a second point on the line. And using this thought process that we're looking at right now is very, very difficult. In fact, for a lot of mathematicians, they couldn't figure it out either. For years and years and years, they knew how important the slope of this tangent line would be, but they couldn't figure it out. They couldn't find out how to find that slope. It eluded them forever. And so what happened eventually is they said, okay, it's impossible for us to find our first point or our second point using what we have right now. And again, we know the point of this line is 1, 2. So here is the idea that they came up with. They said it is impossible to, in general, Like I can draw some lines, and if I draw my line exact, I can tell a second point that exists on it. But by and large, that is a very difficult task that I just can't do every single time I want to find the slope of a tangent line. So here's what they said, and hopefully this kind of makes sense. They said, all right, we are going to cheat just a teeny tiny bit. Instead of us using a second point that exists on that line, what we're going to do is we are going to create a secant line still. So we're still going to have a secant line, but it's going to look like a tangent line. And the way that they accomplish that is they say, okay, my second x value here is going to be 1 plus h. Now you might be saying, okay, well, what is h? Well, in these problems, what we're saying is we are going to take the limit as h approaches 0. And our x value is going to be 1 plus h. If you think about that for a second, what that is saying is I've got 1, and I'm going to put a point that is right next to it, and then I'm going to find the slope between those 2 points that are like right on top of each other. And if I get those points to be close enough, although it will be a secant line, to the naked eye and to everybody, because those points are so close together, it will look like a tangent line. But I want those 2 points to be as close together as possible. That's why I'm using the limit as h approaches 0. Because what that's saying is I'm going to take 1 and add a teeny tiny bit more to it. Well, if that is my x value, 1 plus h is my x value, then finding my y value, unfortunately, is not just saying like 2 plus h. That's not exactly how it works. Instead, I want to be accurate and find the y value that goes with 1 plus h. If my function here is y equals x squared plus 1, or more appropriately, f of x equals x squared plus 1, then if I wanted to find the y value that goes with that, that would be like finding f of 1 plus h, which is 1 plus h squared plus 1. So that would technically be my second y value here. I'd have 1 plus h squared plus 1. So it looks more complicated, but now that we understand that we've got a second y value that goes along with our second x value, we can go about finding the slope even though it's going to look weird. So I've got 1 plus h and I've got 1 plus h squared plus 1. Those are my 2 points. Now again, my second point, if I were to look at it basically with the naked eye, would look identical to the first point because they're right on top of each other because we've barely shifted over just a teeny tiny bit. So now I'm going to try and find the slope. Okay, so the way I find the slope again is we're just going to use, the simple definition, y2 minus minus y1 over x2 minus x1. And we'll use the more complicated one in a minute. My y2 in this case is 1 plus h squared plus 1. My y1 is 2, so I get minus 2 over my x2 is 1 plus h, and my, that's not a comma, I didn't want to put a comma there. Okay, that's not a comma, so then I'm going to have minus 1. One thing we have to remember is that this is the limit as h approaches 0. So if that's the limit as h approaches 0, then what I do is I say, okay, I'm going to plug 0 in and see what happens. So I'm going to get 1 plus 0 squared is 1, plus 1 minus 2 on the top, and then I get 1 plus 0 minus 1 on the bottom. That gives me 0 over 0. Now, we talked about 0 over 0. We talked about it in the last unit, again, bringing previous knowledge back. 0 over 0 is the indeterminate form. That means that the limit probably exists. We just have to do some canceling. So instead of plugging the limit in, what we're going to do now is we're going to multiply out. We already did that already. Let me get to the point. So what I want to do here is I'm going to try and figure this out by multiplying out the 1 plus h squared. 1 plus h squared is 1 plus h times 1 plus h. So if I FOIL that out, I get 1 plus 2h plus h squared plus 1 minus 2 on the top. And then on the bottom, notice I have 1 plus h minus 1. Well, 1 plus h minus 1, the 1's cancel and I'm left with h. On the top, I get 1 plus 1 if I'm trying to combine like terms. 1 plus 1 is 2 minus 2. So all of this stuff also cancels out, and you notice that I'm left with 2h plus h squared on the top. Well, the reason why that's helpful is notice that both of the terms that are left on the top, I can factor an h out of. So I factor an h out of the top once I cancel everything else out. And why that helps me is now an h cancels from both the top and the bottom. And this is the limit as h approaches 0 still. Just like before when we talked about indeterminate form, we saw what canceled, and then we take that value and we plug it back in. So 2 plus 0 is equal to 2. Now, that might not seem like a really big deal, but what you have to realize, what we just did, is we found a way to find the slope of this tangent line that we were talking about right here without technically finding a second point. Instead, we use this formula, do all the math, and we found out that this indeed is, the slope of the tangent line. Every time, that is our slope. Now, and it's not always 2, I shouldn't say that. This process is the way that we can always find the slope of our tangent line. Now, I know that's a little bit confusing, and we're going to do another example here in just a second. Okay, we talked about all these things. Okay, so let's try this next example and see if we can understand it. This time I'm going to say, okay, I'm going to use this technical, my formula here to find the slope. So I'm going to have f of x2 minus f of x1, we talked about this earlier, over x2 minus x1. Now, the 2 points that I'm going to have are 2 and 2 plus h. Notice, again, that I'm just choosing 2 points that are right next to each other. 2 x values, excuse me, that are right next to each other. And if I take 2 and I plug that in here, I get 7 as my y value. Now, if I take 2 plus h and plug that in, I have to take 2 plus h, and everywhere I see x, I have to put in 2 plus h. So I get 2 times 2 plus h. Minus 1. This is the part that takes a while because we need to multiply this out now. So when I FOIL that out, I get 4 plus 4h plus h squared plus 4 plus 2h minus 1. Here I have to combine my like terms. Again, I'm still just trying to find my second y value, my second f of x2, my f of x2 if you will. So 4 plus 4 minus 1 is 7. 4h plus 2h is 6h. And h squared is the only h squared term we have. So the term I have here is h squared plus 6h plus 7. That's my y value for my, that's my f of x2, if you will. So f of x2, in this case, is h squared plus 6h plus 7. F of x1 is just 7, because that's what we got when we plugged in x1. Then I divide that by 2 plus h minus 2. That's x2 minus x1. And again, because we're talking about a limit, we have to include the limit part. Now, this time, hopefully you can see that the 7s will cancel out. So I get h squared plus 6h on the top. And then on the bottom, my x values, the ones that I know, will always cancel out as well. So I've got h. Now, technically, if I plug in 0 right here, I will get the indeterminate form. And that will happen in every one of these problems. So instead, what we do is we say, okay, I'm going to factor an h out. And the reason for that is then the h on the top and the bottom will cancel. So this is the limit as h approaches 0. Now that those h's canceled, I get 0 plus 6, which is 6. That gives me, again, the slope of the tangent line of this function when x equals 2. Which, that seemed to go a little bit faster. And we said, okay, we know what we're doing. We can see that that's how we find the slope of the tangent line at that particular x value. Okay, so hopefully that still makes sense. A couple of things that always happen in these problems that I want to call your attention to. The first thing is when we try and evaluate this limit, I should say the limit, not the function, we get the indeterminate form. That will occur every single time in these problems. That's how they're set up. The second thing is once you factor out all the limits and cross out like or combine like terms and cancel stuff out, there will always be an h that you can factor out at the top of the fraction. Furthermore, because there will always be an h on the bottom of the fraction, they will always cancel. And then once we cancel those h's out, then what's going to happen is we will be able to find out what that limit is, which in turn will tell us what the slope of the tangent line is at that particular x value. Now, I know that's a ton of stuff going on, and there's a slightly simplified version of that, and that is this right here. I can say technically that the limit as h approaches 0 of f of x plus h minus f of x all over h will always yield us the slope of a tangent line at a particular point. The x here is just the x value in question. Whatever x value we want to find the slope at, that's what we plug in right there. And then the bottom is h, because every single time, like if I'm looking at the x value of 3, my x2 would be 3 plus h, my x1 would be 3. So 3 plus h minus 3, the 3's are going to cancel out, and I would just be left with h on the bottom. The same thing would be true if it was 7. You'd have 7 plus h is my x2, 7 is my x1, those would cancel out, and you would be left with h. And that happens every single time. So that is why it's just h on the bottom here. So if we wanted to, we could apply this formula to help us find the slope of the tangent line at whatever x value it is that we are interested in finding that slope at to help us, again, it's slightly simplified. It's still not easy. There's still an awful lot of algebra that's involved, but we can do that. So that is a brief explanation, and that is brief. If there's ever an idea that we've talked about in this class that if you weren't here and that didn't make sense, you'd probably want to come into B time, it would be this one. Because of all of them, this one is fairly hard to understand all of the nuances, and obviously you can't ask questions right now. So if you do have any questions, please come on in, and I will help you understand any misconceptions you might have about this. This is very important for what we talk about in the next section especially. So if you have any questions, please come on in. Other than that, good luck.